All right. So we're going to do a couple of calculation type questions. These are two different types. And the first one here is a question which is example 3 in the textbook. And basically in this question, they have given you given the length of a chord and also the length of the radius. And they're asking key now at the endpoints of this chord, there are going to be a tangent each, right? So this tangent and this tangent, they're asking us the length of this tangent. So they're going to intersect at the common point T here. They're asking the length of this tangent TP. They're asking us what the length is. There's basically another way of looking at it is key from an external point T, we have two tangents coming. These endpoints form a chord here. And we know the length of the radius, we know the length of the chord. What will be the length of these tangents? Okay, that's another way of looking at this question. All right. Now, there are a couple of ways to approach this question. We are going to approach it more algebraically, okay, by using the Pythagoras theorem. But before we do that, we'll have to like establish something right here. So, okay, let's see. Let me just at the outset tell that there is another way of doing it using similar triangles. You can refer to the book for that method. Okay. We are going to okay. Now let's read this question once. Okay, PQ is a chord of length 8 centimeter and circle of radius 5 centimeter. The tangents at P and Q, the tangents at P at Q, there's going to be only one tangent P and Q. They intersect at point P. Okay. Find the length TP. Right. Basically, find the length of the tangent. Now, if you notice, this is not given. Okay, this is the part which they have drawn. This is an example question. I just copied the question from the textbook, copied the diagram from the textbook. Now this is a part which is not there. Okay, so this is a part of a construction, which is a process of solving the process of solving the question. Okay, this all that you see right now is what is given in the question. So first step there is of course to join OT. Okay, our first step is to join OT and let it intersect PQ at R. You can write that or you can just draw it in the diagram. Now when we join OT, like intuitively we know that, oh, this has got to be 90 degree, but that's not the case. Okay, we have to prove it. We have to write show steps that actually this is 90 degree. Only then will we be able to use this right triangle or any other right triangle. Yeah. So we're going to do that right now. Okay, join OT. When you join OT, you check triangle TPQ, okay, or triangle PTQ. Triangle PTQ, this particular triangle PTQ is an isosceles triangle. We already know that because the lengths of tangents from the same side, from the same external point are equal. Is an isosceles triangle. So triangle PTQ is an isosceles triangle. Okay, which since TP is equal to TQ. Why is that? Since the lengths of a tangent from an external point are equal. Okay. Now, since this is a calculation question, you don't have to write all of these steps here. If you write just this much, it should be enough. But I'm just writing for the sake of clarity. So TP is equal to TQ. So the lengths of the tangents from as the lengths of tangents from an external point are equal. Now, if you notice very carefully, what does that give us? Okay, now that also means if TP is equal to TQ, we know that OT is the angle bisector for angle PTQ. The reason is because we have seen this before, that the line joining the center to the tangent bisects the angle of inclination of the two tangents to each other. Okay, this line joining the center to the external point bisects the angle formed by the two tangents from that point. Okay, so OT is the angle bisector for angle PTQ, which essentially means angle PTR is equal to angle QTR, right? Angle PTR is equal to angle QTR. Now I have these two as these two angles are equal. I have this side equal to this side, TP equal to TQ, okay? And I also have this side as common, which means I can show that this triangle is congruent to this triangle, okay, by SAS. So I'm just going to skip the steps of that here. I'm going to directly write, therefore, triangle TPR is congruent to triangle TQR, okay? And you can show it by SAS, okay? We have already shown this is equal to this. These are common, and TP is equal to TQ, we've already shown above. Essentially, where we are right now is that we can say that angle TRP is equal to angle TRQ, okay, which is this angle is equal to this angle, and that's what will lead us to conclude that these two angles are 90 degrees. Okay, angle TRP is equal to angle TRQ by CPCT. Okay, by CPCT of congruent parts of congruent triangles, TRP, TRQ. Okay, going in correspondence there, but angle TRP plus angle TRQ is equal to 180 degree, because it's also on this, these are also angles on this chord, right? And this chord is a line segment. That angle, those some of those two angles have to be 180 degree. Essentially, we get to angle TRP is equal to 180 degree. If you write in place of this, you also write TRP again, so you get two angle TRP. So angle TRP is equal to 90 degree. All right. Now we have come to the point where we can say confidently that this is 90 degree. If this is 90 degree, this is also 90 degree. These two have got to be equal, so these two are also 90 degree. Okay. So all these four angles at point R are forming 90 degree. Okay. Now angle TRP is 90 degree. Now that gives us two right triangles here. This is triangle ORP as well as triangle PRP. Okay. Now, after reaching to this point, what do we think? What do we think we're supposed to do? Okay. So all this for something which we are already intuitively aware of. The reason is because there is no theorem saying that these two will be perpendicular to each other. We have no theorem in our textbook. Actually, it could have been a theorem, but it's not there. So all this drama to get to that point. Yeah. Now, if you take this particular triangle OPR, we know that OR is also perpendicular to triangle. OR is perpendicular to the chord PQ. Now, can we say that? Because this angle is 90 degree, the angle ORP is 90 degree. Okay, we can go ahead, write this. Therefore, angle ORP is also 90 degree, which implies OR is perpendicular to PR. Okay, or we can write OR is perpendicular to PQ. Okay, one second. OR is perpendicular to PQ. Okay, if OR is perpendicular to PQ, then if you notice, OR is also the line joining the center to this chord, and a line segment which is perpendicular and passes through the center. Basically, it is the perpendicular from the center to the chord that's supposed to bisect the chord. So this line segment and this line segment, that's PR and QR, are going to be equal. Okay, therefore PR is going to be equal to QR, as line segment, or you can write it like this: perpendicular from the center bisects the chord. Ninth class theorem. Okay, perpendicular from the center to a chord bisects the chord. All right. Now, what does that give us? We already know that the whole length of the entire PQ chord is 8 centimeters. So that gives us the length of PR. That will be 4 centimeters. Therefore, PR will be equal to QR, or I'm sorry, PR will be equal to QR, that will be equal to 4 centimeter. All right. So we have that now. Now we don't have to deal with this 8 centimeters full length anymore. We have got this length. This is 4 centimeter. Okay, that's 4 centimeter. Now let's see what to do. What do we do going ahead from here? Okay, now once again, let me write this properly. This particular length, this much length is 4 centimeter. All right. Now let's take the right angles which we have here. Okay, we have this right angle triangle, this right angle triangle. We also have this full thing as one right angle triangle, because the tangent is going to be perpendicular to the radius at the point of contact, right? That's another theorem which we have in 10th grade. So looking at all this, now I have to figure out a way in which I can find this length TP. Okay, there's no direct way which is coming to our mind. Okay, but there are a lot of right triangles involved, because there's going to be a lot of Pythagorean theorems involved. So we're going to use those Pythagorean theorems to see if we are able to using some combination of these Pythagorean theorems get to the answer. Okay, so just to make our writing steps simpler, we're going to take TP as X and TR as Y. Okay, I'm doing it exactly as the book says. You can choose to take anything as anything you want, right? So I'm going to continue writing from here. All right, taking TP as X and TR as Y. Let's take triangle TPR. Okay, let's take triangle TPR. That's a right triangle TPR. In right triangle TPR, or you can write in right triangle TRP, just to keep the center vertex, the right vertex in the center. Okay, so we have here x square is equal to y square plus 4 square. Okay, where x is the hypotenuse and this is the right angle. Okay, x square is equal to y square plus 4 square, or you can write x square is equal to y square plus 16. Okay, let's take this as equation number. Do we have any other equation numbers before? Anyhow, let's take this as equation number A. All right. Now, now we have this. Okay, we have other few right triangles also. If we take right triangle ORP, okay, right triangle ORP, we can actually find OR here. We can actually find OR here. This is 4, this is 3, this is 4, this is 5. So obviously it's going to be 3. Pythagorean triplet. If you don't know, then just write it down. So OR square is equal to 5 square minus 4 square. So OR square is equal to 25 minus 16. OR square is equal to 9, or OR is equal to 3 centimeter. The positive root I'll be taking because it's length. Yeah. Now after this, let's continue here. Okay. Having done this, I know the length of this thing also. This is 3 centimeter. Okay, now I have taken 2 right triangles. I have taken the 2 small right triangles. I've taken this one. I've taken this one. Nothing more I can do with this. Here I have 2 variables hanging. Not much I can do. But there is one more right triangle which I can use. That is this. Okay, and that will again use x and y. But it will give us another variable with the 2 same equations, and maybe 2 variables, 2 equations, something can happen. Even though it's looking like it's a quadratic equation, but I think something can happen. Okay, let's move this thing down for now. Okay, so we're just copy pasting it here. All right, now let me move this out of the frame. Okay, so that'll be a little less confused of what is written where. All right, so we're going to take triangle TPO now. Okay, so we're going to take right triangle TPO now. Okay, right triangle TPO. We have TP square, that's x square. Now if you notice, now here the right angle is here. All right, the right angle is at P. Right angle is at P. If you want, you can write that step earlier. I think it's good enough to write that step earlier, or you can just write that step here. TP is perpendicular to, how is right triangle? How is this a right triangle? Because TP is perpendicular to OP, as tangent is perpendicular to the radius at the point of contact. Okay, right. This is the theorem of this chapter in 10th grade. So tangent is perpendicular to the radius at the point of contact. Now, in this right triangle, we're talking about this particular right triangle TPO. I have x square plus 5 square is equal to y plus 3 the whole square. All right, x square, this is one side, one leg, 5 square is another leg, hypotenuse is opposite to this, is equal to y plus 3 the whole square. Okay, so we're going to do that. X square plus y 5 square, x square plus 5 square is equal to y plus 3 the whole square. All right, let's open this up a little bit. X square plus 5 square is 25 is equal to y a plus b the whole square. That's a plus b the whole square is going to be a square plus b square plus 2ab. Okay, so that gives me y square plus 3 square plus 2 into 3 into y. That's basically x square plus 25 is equal to y square plus 9 plus 9 plus 6y, or x square. Let's take 9 to the side. It will become 25 minus 9. You will get 16. You can write that step. X square plus 16 is equal to y square plus 6y. Okay, stay with me here. Let's take this equation b. Okay, now we essentially have two equations and two variables, but they are quadratic. They are not linear. So if you see this and this, there are two equations, there are two variables, but they are quadratic. We don't know a way to solve them, but we know a way in linear equations which can help us solve them. Okay, if you pay careful attention, x square, here there's y square, here there's y square. So if I, on the right side and on the left side there are two x squares, in one in each equation. If I just subtract these two equations, okay, one from the other, I'm going to end up eliminating x square and x square, y square and y square. Okay, I'm going to end up eliminating that, and essentially I'll be left with only the variable 6y in the final equation that I have. Okay, so what I'm going to do now, so what I'm using is I'm using my knowledge or my skill of elimination, which we have learned in linear equations chapter here, to remove this unnecessary stuff, that's x square, y square, and to get to a place where it's easy to solve. Okay, it's a linear equation, one variable. So all I'm going to do is I'm going to say equation b minus equation a. Okay, I'm going to write everything down. Let's not just be confused. So let's write b first. X square plus 16 is equal to y square plus 6y. Okay, equation a, so I have minus x square, and here I have minus y square plus 16. Okay, whatever was in a has come after the minus sign in both sides. All right, since I put it in brackets, let's take things out and let's see how things go. So x square plus 16 minus x square is equal to y square plus 6y minus y square plus 16. X square and minus x square go away, y square and minus y square go away, so I have 16 is equal to 6y plus 16. Sorry, I think I made a mistake here. So this is going to be minus 16, minus 16. So you have minus 16 here. So 6y minus 16, you take 16 to the other side, so I have 16 plus 16 is equal to 6y. Basically 6y is equal to 32. I get y is equal to 32 by 6, that's equal to 16 by 3. All right, but I don't need y, I need x. I got y here. I can use, I got y, but I don't need y, I need x, because the question is asking me to find the length of TP, that is x. Okay, so let's look at this question again. Let's look at the equations we have. We can find x through any one of these equations. This one is there, this one is there. Use any one to find x. We'll use this one. This one looks simpler. So I have x square is equal to y square plus 16 is my equation. Equation A. So in A, x square is equal to y square plus 16. I'm just copying this equation from here. X square is equal to y square plus 16. Okay, y square, y we know the value is 16 by 3. So we get x square is equal to 16 by 3 the whole square plus 16 solve this out. So one thing you can do is 16 into 16. You can do that. 16 into 16 is 250. I don't really remember. Let's do it a simpler way. Okay, let's do it like 16 into 16 by 3 plus 16. There's also a way the book does it. Okay, just to make this calculation easier, they take 16 common outside. So you have 16 by 3 plus 6 plus 1 in the bracket. Okay, 16 by 3 plus 1 in the bracket, because we're taking common 16 common here. So 16 is a factor, 16 common outside. Here also 16, they're taking factor, 16 into 1 is there. So I have only 1 remaining in the bracket. Okay, 16 by 3 plus 1, that gives me 16 into 16 plus 3 by sorry, I have made a mistake here. I have made another mistake here. Okay, I have not multiplied the squared of the denominator. Okay, so you have 16 by 16 to 16 by 3 into 3, right? So that gives me, again, doing the same process though, 16 common, I have 16 by 9 in the bracket plus 1. Okay, see, I'm taking 16 common out. I'm left with 16 by 9 plus 1 from here. So that leaves me with 16 into 16 plus 9 by 9. That's equal to 16 into 25 by 9. 25 multiplied by 4 is 25 multiplied by 4 is 100. So 25 multiplied by 4 into 4, that's because this has two 4s. So this is 100, 400. I'm getting 400 here. 400 by 9. That's x square. Hold on, stay with it. Okay, that's x square, that's not x. So x square is equal to 400 by 9. Now I've got to take the root on both sides. So x is equal to, and if you take the positive root because it's distance at the end of the day, this root over 400, you can actually, we could have factorized it here only instead of going all the way and multiplying. But nonetheless, let's do 400 is actually 20 square. We are very familiar with it. This is 3 square, so you get 20 by 3. Yeah. So TP is equal to 20 by 3 centimeters. You can change it to decimal if you're interested. This is also fine. Okay, completely fine. So that was question example 3 for you. A little long, quite long actually. All of these steps that are involved are essentially would have not been necessary if they would have just made a theorem out of this fact that the line joining the center and the external point will be perpendicular to this chord formed by the endpoint, formed by the points of contact of the tangent from that point. But nonetheless, we have this here, so we had to do this all the way to get to these two triangles being 90-degree. And then we had 3 right triangles. We used those 3 right triangles in all ways we could, and we ended up with having 2 variables, but quadratic equations. We eliminated those squares, x square and y square, and finally came down to finding 1 variable in one equation. And after we got that, we put that in the other equation to find x. Yeah. No, it's a little bit long. Maybe you can go through it again if it's troubling your mind. We'll do one more question following this, which is a little long. Yeah, that's all for this class.